Hi, my name is Naveen, and today I'm going to be talking about my lab number 5 for Physics 2212. Introduction. So the purpose of this lab was to explore the forces created by an induced EMF. A model was created to predict how an induced EMF would have an effect on the motion of a bar magnet. The bar magnet we used for lab 3. So the physics principles involved the Oates-Savart law, specifically changed from magnetic dipoles, especially derived for magnetic dipoles, and Faraday's law. So experiment observations, these were my test times. The magnet I used was not particularly powerful, so the test times were pretty low. Model. So these values are the dimensions of my aluminum foil roll. The length was 12.5 inches approximately, and I converted all the values to meters. I changed the mass values according to values I found from a magnet online, and then the dipole moment I just got from the previous lab where I derived it. I just set bar mass to mass for my own convenience. That's not something that was necessary. It's just my own visual clarity. And then next I updated the dipole B function with the formula for the magnetic field of a dipole on axis. Just copying of a formula. And then next I changed the deflux dt calculation function. This formula was just updated to be consistent with the formula for deflux dt for induced EMF in a ring due to a dipole on axis. There was some weird stuff I had to do here. So for the distance formula, I had to find the vertical distance, and that's how I did that. I did the absolute value of the difference in y positions. Yeah, and this function was just updated to reflect that. Next, I updated the f-grav formula, which is just a vector 0 negative bar mass times g and 0. And then next, I just defined r hat and r mag for my own convenience, just after finding r underscore ring. So next, I changed the b at ring formula. This is the same formula used as before. It's just the magnetic field due to the dipole, due to the bar magnet at the ring. So after that, I found b hat so I can use it to find sine theta. Sine theta is just the magnitude of the cross product between the unit vectors of the dipole moment and b, the magnetic field at the ring. And then after that, I used all these values to find the magnitude of F on the ring due to the bar magnets. Then I changed the F net formula and then updated the bar dot vel and bar dot position equations according to Newton's second law. So the result I got was that my time was 0.362 seconds, which was significantly lower than my experimental data. I don't know what that is actually. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? The current would be extremely high since resistance would be extremely low. This would increase the force exerted on the magnet by a lot, and it would pretty much make the magnet get pushed upwards since the current is infinitely high. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be less complete rings and the current would be lower. The current only flows in the clockwise direction. There's no vertical movement of it, so it literally interrupts the current, and therefore there would be the current would be just lower overall, and this would decrease the force on the magnet.